Hi guys, welcome back. I want to introduce you to the lab for this week, which is about converting analog signals to digital signals. Now we've already done that to some degree using the analog to digital converter, but this is more of a time-based thing. We're going to see how you convert analog signals immediately into digital signals using something called a comparator. So let's take a look. This is what the circuit we're going to end up with looks like. In broad strokes, we've got an analog signal coming in. We're comparing that signal to another analog signal, V compare. This is V in, V compare. A comparator is a device that puts out a high voltage when the not inverting input, the plus input, is greater than the minus input, and it puts out a more negative voltage, in this case 0. It's going to flip between 0 and 3.3 volts. So if the positive input is greater than the negative input, it'll go up to 3.3 volts. If the positive input drops below the negative input, it's going to go down to 0, and it just toggles back and forth. We're going to use that toggling digital signal as a clock to a 3-bit counter. So this guy counts from 0 up to 7 and then back to 0. This is the least significant bit, this guy. This is the next significant bit, and this is the most significant bit of the 3 bits. And we'll be able to see those bits on these pins, pin 1, pin 2, and pin 3. So the way it's going to look is if this guy cycles 10 times a second, this guy's going to cycle 5 times a second. This guy will cycle, this one will be 2.5, and this one will be 1.25. Or I guess I should have used a power of 2. Let's say this one comes out at 16 cycles per second. This will then be 8, 4, and 2, like that. So each one will essentially divide the frequency by 2, because it's a flip-flop that's designed to toggle in that way. Okay. So, but we're not going to just build this circuit and then test it. We're going to build it one component at a time. So let's go ahead and do that. I want to walk you through how that works. So let's close this workspace. And I'm just going to create a brand new workspace. So create a project. And I'm going to target the same module we used last week, the 416.045-2. Instead of picking a code example, we're just going to start with an empty schematic, and we'll just take the default. So I'm going to call this thing Project 6. Let's see if I can do this. Okay, I guess. Okay, so it's a completely empty project. Now the way this interface works, we can go over here and grab things. So what I want to do is to grab an amplifier. I'm just going to start with the amplifier, and all I want to do is validate that the amplifier is working correctly. So let's move in here. I'm going to need a couple of pins to do that. So under ports and pins, grab a couple of analog pins. So I'll grab one for the output, and I'm going to grab one for the input. So we're going to call this one V in. We're going to call this one V amp out. Okay. And then I'm just going to wire those guys up. So V in is going to come into the non-inverting input, and V out is going to come from the output. And what about this guy? Well, I want to set this thing up in follower mode, which means the output is going to the output pin is going to connect to the inverting input. So it becomes a follower, a unity gain amplifier, gain of 1. And the output drive, we want to actually make this be able to go to a pin. So let's go ahead and build that. Okay, so I'm going to go ahead and click the button here to generate the application. That's going to go through and synthesize all the connections needed. Literally all I'm doing is making a follower, and I want to just check with the oscilloscope to make sure it follows. That's the idea. What I want you to do with these projects, I encourage you to always do with all your projects actually, is don't just spend a long time building a complicated project. build the smallest piece of it that you can test. And once you've got that piece built, test it. Make sure it works. As soon as that thing works, then you can go on and build the next part. But don't build 5 pieces that go together and then turn it on and now it doesn't work. And now what do I do? Well, I've got, there's 5 pieces or some combination of pieces. So what are there? 5 factorial ways that can break or something, right? So it maybe it's not 5 factorial, but it's a lot of ways, and it's very difficult to debug. And so if you just build one thing at a time, test that one thing, you'll get a lot more progress for the time you invest. So that's just a bit of philosophy there from your friend Dr. Spickelmeyer. Okay. What I want to do is open up the source file here. I've got an amplifier, and it turns out, I'll just point out, if you open the datasheet for the amplifier, one of the things you'll find in the datasheet is a list of API functions. So here we are. This is in follower mode. So and this describes all the things you can do with the amplifier and the different modes of operation and so on. But if you look in the datasheet, you'll find the application programming interface. So that's the set of functions you can call to run the amplifier. And one of the things you'll find is that the build system, let's see if I can find it here. Well, this particular one doesn't seem to have exactly what I'm looking for. I'll show you where else you can look. You can find it. Yeah, I'm looking for a function. Here we go. So this is part of it. You can call this function to initialize the amplifier and call this function to enable it. But it turns out the IDE, the PSoC creator, helps you out a little bit in that regard. You don't really have to do all that. So what you can do is notice that there's the folder for the op-amp files, and there's opamp1.c, opamp1.h, probably an opamp1. I just missed it the first time through. Opamp1 start. That's what I want. That function actually calls all the other functions you need in order to get the thing going. So we can simply go into our main program, and before we get into that main loop, we can say opamp1. And then if I just type S, it shows me there's the opamp1.start. So I can just double click that one and save it. And then if I go ahead and build the application and program it, let's see, it's saying it doesn't see the board. Let me see if I can, maybe I have to re-plug it in here. Hang on. Connect to Windows. Okay, that looks promising. Oh, I realized something. It says kitprog 3 version expecting 2.1, but found kitprog 2 version 1.05. So I'm going to show you in a minute how to use the programmer GUI to upgrade that. Actually, let's do it right now. If I click on this guy, there's the programmer. So these boards that I just opened in new packages, it turns out that evidently they aren't actually updated. So if I go to Utilities, I go to Upgrade Firmware. Not connected. Yikes. Maybe I need to close out of this guy. Let's see. Let me try to program it with the old version first. So complicated. Okay, it's going to build it. It's building the M0. I've already got the M0 core programmed on this device, so I don't need to really worry about that. It's the M4 I care about. It always takes a while the first time. Once you're in the groove and you're making changes, it builds pretty quickly. There, so it actually built it. So let me, actually I'm going to close this. I'm going to reopen the programmer here. I'm going to try to connect again. Not connected, utilities. Oh, I got to click that guy. Okay, there we go. That was the problem. I didn't click the kit prog. It says yes, I want to connect to Windows. And let's see if that op amp works. Okay, let me reload the project. I think it was in Workspace 2. There we go. There's my op amp 1 start. There's my design. So let's go check the pins and see. So I'm going to click on the pins tab here. Let's open that guy up. Okay, so Vamp out is pin 9.2, V in is pin 9.0. And I'm going to go ahead and lock those in. So if I connect wires to them, I don't have to reconnect all the time. So let me go over here. Hang on. Okay, so now I'm over looking at the oscilloscope. That sinusoid you see there is my input signal from the function generator. And what I want to do, let's do this. That's going to go over to pin 9.0. So let me plug that back in again so you can see it. So there it is. That's the sinusoid from the function generator. Let's put the other trace of the oscilloscope on the output, which is pin 9.2. So 0, 1, 2, that's right here. Where did that go? Oh, it's right on top of it. So it's 1 volt. They're both on the same scale. They're both on the same. Let me move trace B up so you can see it. Okay, so that amplifier is working because you can see trace B shows exactly the same as trace A. If I move the function up and down, if I change its amplitude, it just follows along. So it's following exactly as it should. Okay, so my follower is working. Perfect. So now let's add the comparator. So the comparator is this guy. And what I want to do, let's I want to just steal the signal right from there. And I'm just going to join this guy here. Okay. So, and then this one I'm going to need a digital output pin because I want to watch the output of that comparator. And let's just do it this way. Okay, but I need a voltage to compare it to. So the easiest thing to do is to grab a voltage from my board. So in the lab, you guys could use the DC power supply on the bench. You could use a couple of resistors to build a divider. There are some reference voltages built into the toolkit here, but I just want to reduce the number of things you have to learn all at once. We can just make another analog input pin and make this be our V-compare, CMP. So that's our comparison voltage, and we'll just run that into the comparator on that other pin. So somehow I got, hang on, that little bit, there we go. Okay. And okay, perfect. And then this one, we actually want it to go, it's digital hardware connection. Yeah, I guess that's okay. So let's go ahead and try to generate this design. And what I'm going to do is grab, I've already got a little divider set up on my board here, so I'm just going to grab that output of that divider voltage and use that as my V compare. So let me, let's see, I'll put that, let's get that for trace B. Here's my divider. And I've got it on a little potentiometer, so you can see right now it's at about, a volt, but I can move it up and down. So there it is. I got it at about 1.5 volts. I can take it down here. I can make it 0.5 volt just by adjusting that potentiometer. But of course, if you had a couple of fixed resistors, you could still get a divider and get pretty much any voltage you want. I can bring some potentiometers to the lab on Thursday if anybody wants to try using one of those guys. And of course, you can also just use the bench DC supply. So you just connect ground and connect the output of that DC supply, and then you can adjust it to whatever voltage you want. Okay, it looks like that built okay. So I'm going to go, now here's the thing, I've got another device. So now I've got to go back to my source code, and I've got to turn on that comparator. That comparator needs to be initialized. Luckily, again, you'll notice when we added the comparator, what we ended up with in our source tree is another folder with comparator1, a comparator1 header file. And in that comparator1 header file, there should be defined a function, which we can call to set things up. See if I can find it this time. There it is, comparator1 start. So I'm just going to grab that guy. And we'll go back to main, paste that. Okay, and that will fire up the comparator. So that should do it. Let's go ahead and build. Okay, it did it. So now let's see what we got here. I want to, instead of looking at the comparison voltage, I want to actually look at the comparison output. So let's pop back over to our pins. And the compare output is now P9. V compare is the input comparison. That's P94. So that's 0, 1, 2, 3, 4. That looks good. And then let me just check. The amp out is pin 2. Is that still there? Yes, that's still there. And comparison out is pin 1, and that's 9, 3. And there it is. The comparator is busy comparing, and you can see that when the sine function goes below the threshold, the output goes low, and when it goes above the threshold, the output goes high. If I can move the sine function up, remember it's right around 1 volt. You can see it's just passing over. Now if I bring it down, it's doing the same thing. I'm losing my trigger because I'm triggering on the sine. You can see there's a little bit of noise there, but the basic functionality is there. So I've got my I've got the op amp and I've got the comparator. So now what I want to do is let's add a couple of those flip-flops. I'm not going to add every single flip-flop. You guys can add flip-flops. I just want to show you how it's done. And then you can add the other 3, and then also the AND gate. So the AND gate is here. I'll let you get that. If you click on it, you can see the image. Basically, it takes 2 bits in, and it puts out a bit that's high if both of the input bits are high. So it takes 2 logical inputs and produces 1 logical output. The toggle flip-flop is an interesting flip-flop. It has a clock input, and then it also has a T input. When the clock input transitions and the T input is high, the output toggles. If the clock transitions and the T input is low, the output doesn't toggle. So it toggles or doesn't toggle depending on whether the T input is high or not. So what we do is we take a logical 1, a logical high, and for the first flip-flop, it always toggles. So it toggles no matter what, whenever the clock goes. So what I'm going to do is grab here. Okay, and then I'm going to get another output pin, a digital output pin, and put that guy here. and then we'll check to see if that guy's toggling correctly. Let me go ahead and build the design. Now the nice thing about toggle flip-flops is they're so dumb you don't even need to configure them or init them or start them or anything. They just work. Same way with the AND gates. So any of these digital logic devices don't really require any configuration. They're not that configurable. They just do what they do. So it doesn't require any change to source code, so we don't have to recompile. At least I hope we don't have to recompile. And so it should just work. Let's try it. There it is, pin 5.2. That's our friend. Let me go ahead and turn down the time base here a little bit. That's the output of the comparator. Pin 5.2 is pin 1. So that's this guy. No, I'm sorry. That's this guy, the output of the comparator. And then pin 2 is going to be the next one down. That's going to be the output of that T flip-flop. And then now the thing is, I'm triggering on the sine wave, and sometimes the sine lines up with one, and sometimes sine lines up with another. Maybe I should trigger on the. Let me switch the trigger to trigger on the other channel. That's a little more stable now. Now the point is, now that we're triggering on the output of that flip-flop, we're triggering on this signal. You can see that the sinusoid makes 2 cycles every time the flip-flop goes once. And the reason for that, of course, is that the sinusoid is driving this comparator, which is driving this clock. And every time the clock goes low, the flip-flop toggles, so it changes state. So, or actually, let's see, does it look like it's every time the clock goes high, it changes state. So it's going from low to high. So that clock edge, the comparator is going high when the sinusoid goes above the threshold, and that's what's making the thing tick. Now you'll notice if I adjust, I'll go back here, and if I adjust the level, it's not going to affect this output. It's only going to affect the other one. Okay. Oh, okay. So that's pin 5.2. And notice if I shift the sinusoid up and down, it changes the width of those pulses. So that's having a direct effect because that's the direct output of the comparator. But if I move down to the output of that flip-flop, and then I change the sign up and down, doesn't do anything. And the reason is, of course, the flip-flop doesn't care what the duty cycle of the output of the comparator is. It only cares how often it ticks. And so how often it ticks just depends on the frequency of the sinusoid. It doesn't depend on the level or the threshold or any of that stuff. So, okay, that's the main idea. So from here on, you guys just need to, hang on. So from here on, you guys just need to add 2 more flip-flops and that AND gate to match the original circuit. Also, I should point out, what's on GitHub right now is slightly different from this. And I'm going to modify it to match what we're doing on Thursday. So it'll be fixed by Thursday. But Analog Meets Digital, that's the name of the project. We used a different device last year. It was a PSoC-6, and it had amplifiers with the ability to go in and set the gain. But the PSoC-6 doesn't have these, so we just turned this into a follower. Also, the PSoC-5 had a thing called a wave DAC, which let you generate sinusoids and other kinds of wave functions. But the PSoC-6 doesn't have that either. The PSoC-6 has some cool things. It's got 2 processors, it's got BLE, but it doesn't have as many internal devices. So we're just using a follower here instead of a gain of, I think 2 is what I used last year. And the comparator is the same, except we're going to set the reference voltage externally. So we connect this to a pin. Everything else is the same. So if you want to get ahead and read what's here, you can certainly do that. But I just walked you through the process of creating the circuit, so that should be okay. Yeah, last year we used the 5LP, which is a different device. Let's see if that link still works. Yep, it's a different device. This year we're using the PSoC-6. So, okay, that's all I have for you. We'll see you guys on Thursday.